Okay, yeah, it's recording now.
Okay. Okay, so we'll be presenting on Deformable DETR. The presentation is by myself and my fellow group members, Jacob Pfaffenbickler, Tristan Dubligier, and Jacob O'Quinn. Okay, so first I'll briefly show you the outline of the presentation. We'll start with the introduction, then we'll talk about related work, which consists of two main points, deformable convolution and multi-scale features. Third, we'll talk about the method, which consists of the deformable and multi-scale deformable attention module. Third, we'll talk about the workflow, which is the end-to-end process of the deformable DETR. And lastly, we will share our results. Okay, so the problem we're trying to solve are DETR's main problems. If you recall in the paper, we discussed that DETR has two main problems, and it's an ability to converge quickly. So it requires a lot of epochs to properly train. And secondly, it has poor performance on small objects. The authors in the paper mentioned that they want future work to build on this. And the solution, it will be deformable DETR. Briefly to review DETR architecture, in case you need to remember, first it uses a CNN backbone to produce the input feature maps. Second, it uses multi-head self-attention module and the transformer encoder decoder. Third, it uses the FFN to predict the bounding box locations. And fourth, it uses the loss computed by bipartite matching. In our paper, the second point is the one we are replacing with a novel idea in order to improve the results of DETR. So as I mentioned before, in the related work, there's two main categories. First is the deformable attention module, inspired by deformable convolution, which we will explain next. And second is a multi-scale feature map aggregator attention mechanism. Okay, so a deformable convolution is probably new to everyone, or most people here. So in a standard convolution here, we have a rectangular kernel where, for example, we know how to compute a convolution. Every pixel, we have a corresponding point in the kernel where we do a weighted multiplication. But in the deformable convolution, it's not the case. In the deformable convolution in this kernel, there are various offsets, and these offsets can be decided arbitrarily. And for example, we can have symmetric offsets, or we can have seemingly random offsets. So in deformable convolution, we want to change the way we represent the geometric transformation to account for variations in scale or pose or some sort of deformation. So this gives us greater freedom in our ability to represent geometry. So how do we compute the offsets? Well, the offsets are computed based on the input feature map. From the input feature map, we have some additional convolutional layers that will help us compute a 2x(n) offset field. It's 2x(n) because we need an x and y value for the offsets. Each offset is a vector with an x and y, and each pixel in the image needs this offset. So these offsets are going to be used once they're computed through some convolutional layers to perform the deformable convolution for a specific position. We know it's offset, so we know how to do the deformable convolution. But so I will show you the difference in deformable convolution with standard convolution and try to explain to you what's better. So here, for example, on the animal on the left, if we want to compute this pixel is takes signals that are weighted based on previous convolutions. And these previous convolutions are rectangular in shape and in size. So for example, they are for a particular image here, they are all the same size and they are all rectangular. But on the right-hand side, we can see that it's not the case. It turns out that the deformable convolution will more closely follow the outline of the object itself. And we can see that for the animal on the left and on the animal on the right, which are different sizes, this particular point is building off of locations that are more evenly spaced out. And we can see that, for example, while here there might be grass pixels that are involved in computing this point, here it's not the case. They're all kind of following the outline of the object itself and its scale. So it turns out that the deformable convolution helps improve our results. Okay, so multi-scale features. One of the main difficulties in object detection is detecting the various scales, and there's a lot of work done in this area. So for example, to show, here we have various people, and all these people have a different size because they're all a different distance away from the camera. But we want to detect all of them. We want to detect this person, even though they're much smaller than this person. So the previous work attempt to automatically detect the scale or search of multiple scales. Some examples of these previous works that you might know are SIFT or FPN. To show you with an example how this works intuitively, if we take an image and we reduce the resolution by half, for example, so here we have an image of a zebra's nose. And every time we reduce the image by half and get a different image like this, if we think about what a horizontal rectangular bar in the feature map might look like, for the large image, it might even catch the hair on the zebra's nose. On a smaller image, it might be referring to a stripe. On an even smaller image, the horizontal bar might be the entire animal's nose. So this is why we want to represent, we often want to represent images in multiple scales to be able to extract the correct information at various levels of detail. The solution that will use both of these concepts is the deformable DETR. We want to recreate the transformer encoder and decoder using the multi-scale deformable attention modules, and I will pass on to Jacob O'Quinn to explain the method.
Okay. So the DETRs have been shown to require many more training epochs to converge when compared to other state-of-the-art object detectors. This can be attributed to how difficult the attention modules are to train. Taking a look at the self-attention encoder in the original DETR, let this grid represent some feature map that was extracted by a CNN backbone, and the values inside each represent the weight that this particular query in orange has put onto that location. At initialization, the attention weights of the entire feature map will be the same value. However, it is common by the time training ends, the attention maps become very sparse as the model learns to focus on just a few object extremities that are most important, seen here in blue. Meanwhile, the rest of the attention map weights approach zero and essentially are getting ignored by the model. The authors of this paper thus propose a new approach, deformable attention, that takes advantage of the fact that DETR prefers just a few key sampling points. What if we just started off paying attention to a small fixed number of key locations? For this example, we use k equals 3. These key locations are randomly selected at initialization. And during training, we would adjust each key location's offset from the reference point to find the ideal positions to pay attention to. While this technique does result in a great deal of the map being completely ignored, that was essentially what was happening with many of the weights in the original self-attention mechanism. So why would we even want to bother with an approach where we're giving up information? Well, training a model with this approach, all we have to do is learn a few offsets and the weights at those offsets, which results in a great deal of time saving. So for some input feature map with C channels and a height and width of H and W, using the original DETR self-attention, we would have to look at every other spatial location, meaning for one query, we have to check height times width positions. So since we have to query over every single position, it results in quadratic runtime. However, for the new deformable attention module, we're only checking k spatial locations. So and each of these positions has C channels. So one query only takes k times C time. And since we query over every spatial location, we're left with H times W, which is the number of spatial locations, times C times K, which is linear with respect to the size of the feature map. Now that we've gone through how and why we use deformable attention, let's look at an example. So here we're given an input feature map X, which is a height, a width, and a number of channels, and a query that we're looking at. This query has a X and Y coordinate on the feature map. It also has content features, which we'll use to get offsets that we're interested in. From the reference point, we'll apply some offsets calculated by passing Z through a linear network. For this example, you can see we're still using 3 sampling points. So what exactly are the point of these offsets? The model with these offsets is trying to learn which key features it should analyze to detect a particular object centered at this reference point. For example, this combination of offsets might be really good at detecting cow-shaped objects and has learned exactly where in the feature map it should look to detect the cow. However, it's obvious that there's many more things to detect than just 4-legged animals, which is why we can't limit our attention to a single object. Here we introduce additional heads, which can each on their own learn different objects. Here we're using 3 heads. In the actual implementation of the paper, they use 8. We can then extract each key sampling point and then multiply each key by its respective attention. So for example, in the first head, this point that's pointing nearly directly up has been given a weight of 0.5. And after we apply attention, we get 1 value for each head. These values are then passed through a linear network where we get an output of 256 channels. So what do we do with this output? Well, in the encoder phase, this output becomes the value at the reference point in the next layer of the encoder. And then during the decoder phase, this output is used during cross attention between object queries and the output of the encoder to adjust and optimize where we're predicting bounding boxes to be. We'll discuss more of that when we get into the model. One limitation of this current design is that we're only allowing feature maps with the same height and width. Why is this bad? Well, having a mix of low and high level features provide better insight for the model. However, such feature maps come in different scales. In order to take advantage of different feature maps and their different scales, the authors propose multi-scale deformable attention. The only difference between this approach and the deformable attention we just covered is that for a query, we are going to perform deformable attention on points sampled at each scale in the feature map. So for example, in order to calculate this query, if we have k equals 3, we will sample 3 points from each feature map. So we will get 3 low-level features, 3 mid-level features, and 3 high-level features. We would then calculate attention using a total of 9 sampling points. One thing to help contextualize this process is if we were to set, instead of doing just 3 sampling points, we sampled every single spatial location on each feature map, we would actually get back to regular transformer attention. So as we increase k, we're getting more sampling points. We get closer to regular attention, and our runtime gets slower as a result. Now I'll pass it on to Tristan to discuss how these modules are implemented into the model.
Okay, let me share my screen. Okay, so now that Jacob has covered for you, the technical aspects, the operations, and how we're improving a model, I'm gonna walk you through the workflow of the model and step by step how we're implementing all of that. So we start with a ResNet, a conventional neural network, and from there, this is where we're gonna want to get our multi-scale feature map. And we're going to use that as our input for our encoder. And the output of the encoder is going to become the input of the decoder, of course. And then the output of the decoder is going to be our prediction boxes. So the first question is, how do we get from a ResNet to multi-scale feature map? So the explanation is quite simple. When we have an image put into our input, we have multiple stages of conventional, and then we have our fully connected layer. So we pass through 1, we pass through 2, we pass through 3, and after 3, we're gonna apply a conventional operation to get our first feature map, which is the largest one. We're gonna pass into the 4th stage, do it again, and then on the 5th stage, we're gonna do it once and then another time. So to explain you those operations, here you see stage 3, 4, 5, as explained before. And we just, for the 3rd stage, we're going to apply a 1-by-1 convolution with a stride 1. It's going to give us our largest feature map. And then for the last one, we're going to apply a 3-by-3 convolution with a stride 2 to get our smallest feature map. So here you can see it's 1/8 of the height and 1/8 of the width. Here it's a 64th. So you can see the different sizes. So now we have a feature map, we're gonna pass that into the encoder. As explained by Jacob right before me, we're gonna apply the self-attention on our features, and we're gonna apply that until our multi-scale feature maps are fully encoded. and ready to get into the decoder. So what does this look like in terms of images? And let me kind of show you this. So we have our reference points here, and in blue and red you can see the, sorry for that, we can see the offsets. So the offsets are colored by their weights, their attention weights, which is, you know, blue for low and high for, and red for high. So here you can see a reference point being on one of the zebras. And because, you know, the model is being trained, we can see that most of the offsets are actually on the zebra itself. And then we have, you know, high attention on, most of the high attentions are on the zebra. And then we have, you know, outliers all around the image, which are less important. So then if I put a reference point on another zebra, I have the same results. And there goes for the last one, same results. And that, of course, doesn't work only on zebras. We have other examples where we have a computer screen, a laptop, and a cat. And again, reference point on the object and most offsets on the object as well. And same results for another example. So now that we have that, we're gonna want to pass that into our decoder. So we have two main steps of the decoder, which is we have the cross attention, which is passing the multi-scale feature into the object queries. That is quite the same as what we had in the DETR, except this time we actually have multi-scale feature maps. So we adapted it to, of course, handling multi-scale feature maps. Then we have, inside the decoder itself, we have what is called a self-attention. And then we just perform it between the layers of the decoder on the object queries. And it's the same as before. Another thing I wanted to add is we removed the FPN because we were getting, it wasn't improving our score. So we're directly getting production boxes outside of our decoder as an output. So let us look at what it's looking like on the images. So here you can notice the same thing as explained in the encoder, except we have a prediction box with, you know, a prediction and a score. And we have that on a large object, but if I try on the two cars next to it, it works as well. As you can see, this one is right here, and the smallest one is right here. And it has, you know, a small prediction box, which is what we want. So no problem to say it here. And then other examples with a motorbike and two people on it, and more cats and more TVs. So this is our workflow. But then something I wanted to add is we actually have a lot of computing power left, I would say, because basically because of our improvements in deformable convolution and, you know, reducing the number of offsets, we have more computing power that we can assign to other things to improve our accuracy. So the first thing I want to present to you is called the iterative bounding box refinement. And it's actually quite simple. So we're not going to change the encoder, we're going to change the decoder. So for each of our reference points, we're going to set, you know, a small box of the same size always. It's 0.1, 0.1 for the dimensions of width and height. And here you can see, of course, for predicting zebra, it's a pretty bad score. So this is my first layer of my encoder. And then I'm just going to go layer by layer. So here I'm on my third already. And slowly I'm going to improve with training. I'm going to improve my prediction until I get to the end of my decoder. And that's going to be my output prediction box. Another thing I can do is make it a two-stage deformable DETR. So here I'm going to, in the encoder, I'm going to take each pixel and make a small prediction as a bounding box. And I'm going to skip the decoder and give that as my output. Of course, I'm going to compare the scores, and a lot of bounding boxes are going to have poor scores. So I'm going to remove them. and keep a handful of predicting box and box. And I'm gonna pass that into another decoder, which is gonna just do iterative bounding box refinement, which I just explained in the last slide. This is of course more computationally heavy, but we're gonna explain the results of such methods and more Jacob P. So I'm gonna let him share screen.
Unmute. Hello, can everyone see my screen?
Yes.
Okay. Hello, my name is Jacob P, as Tristan just said, and I'm going to be going over the experiments and the result that the authors performed with this paper. But first, I'm going to be going into the background of the experiments. For the data set, they used the COCO 2017 data set, a popular data set used in object detection. For the with the implementation of the data set, earlier on, Jacob mentioned the number of attention heads, which are set to H, which are 2. And for this, the key sampling points, or K, will be set to 4 unless specified otherwise. For the hyperparameters, they used the same hyperparameters as used in DETR, with 2 exceptions. Focal loss with a loss of 2 is used for binding box classification, and the number of object queries was increased from 100 to 300. For the actual training, the epochs used are 50 unless specified otherwise, and after 80% of the epochs are run, no matter which data set with number of epochs is used, my bad. So after 80% of the epochs have been run, the learning rate is decayed by a factor of 0.1. So in this case, it goes from a learning rate of 10 to the -4 to 10 to the -5. For the studies, it uses a ResNet for the CNN backbone. It uses a ResNet backbone. And finally, to evaluate the runtime, NVIDIA Tesla V100 GPU is used. On to the experiments themselves. First of all, I want to quickly run down the different methods that are used. First of all, we have the methods that were first analyzed in the original DETR papers, the faster RCNN with the FPN, DETR itself, and DETR DC5, which is a more accurate but more costly variation of DETR. Second of all, we have DETR DC5 run at 50 epochs as opposed to the original 500. This plus signifies that unlike the original DETR DC5, this one is run using the 300 object queries as opposed to 100. And then finally, we have deformable DETR performed on 50 epochs and then we have 2 variations on it, one that uses iterative bounding box refinement and the other using 2-stage deformable DETR, which Tristan brought up earlier. As for the runtime, when it comes to the floating point operations per second, or flops, due to being slightly more advanced, the total flops is slightly slower. There's slightly less gigaflops per second, but it's still relatively comparable. The training time, however, is where everything really comes to light. Obviously, something using 50 epochs as opposed to 500, it's gonna hopefully take shorter. However, it takes over half the amount of time as DETR DC5 does, even at 50 epochs, which is due to, as they say, we're not focusing on every point, we're just focusing on key points. As Tristan said, 2-stage deformable DETR is slightly more intensive, but still relatively comparable to DETR DC5. As for the inference FPS, like I said, it is faster because we're not looking at every single point. However, there are some unbound memory checks, which is why it is still slower than faster RCNN on average. As for the accuracy, right off the bat, DETR DC5, the regular average precision is already comparable to DETR DC5 running at 10 times the amount of epochs, so 10 times the amount of training, which means that compared to it only on 50 epochs, it blows it out of the water. And then I really want to highlight the AP small, or the precision on smaller images. Because we're using these different bounding boxes, it is better at detecting smaller images. It is more comparable to a faster RCNN at comparing to these smaller images. And then, as Tristan said, using iterative bounding box refinement and then 2-stage deformable DETR gives us the best accuracy. To highlight this increase in accuracy again, I just want to refer to this convergence chart. As you can see, because it's faster to reach its maximum point, it reaches the wanted accuracy much faster. This jump, by the way, is that decay. This is a decay in the learning rate where it changes from 10 to the -4 to 10 to the -5. Next up, I want to talk about the ablation study, which is the removal of features to see what will happen. In this case, we are moving the MS inputs, the MS attention, and the number of key sampling points, or K. We're changing that from 4 to 1, as well as the use of FPNs, or in these first 4 cases, the lack of use of FPNs. First, I want to begin with the first one, where having MS attention or MS inputs and having K of 1, it kind of generates back to a regular convolution, which is why the accuracy is so much lower. But once we add in multi-scaled inputs, the accuracy shoots up by 1.7%, and by using these differently scaled inputs, you can see a very high increase of the smaller images, going almost 3%, and then changing from the number of key sampling points, and then finally going to MS attention, we reach our accuracy that we obtained earlier. So, and then as Tristan mentioned earlier, FPNs are not used. We're not featured in the key experiment because there was very little increase in accuracy, if at all. Finally, we have its comparison to state-of-the-art models, which, as we can see here, first of all, we have these 4 models here, which were created within 2 years of this paper being made, as this paper was presented in 2021. So we can see here, each of them using a different CNN backbone. And then over here, we have if it uses time test arguments, such as horizontal flip and multi-scale testing. And then down here, we have 5 variations of deformable DETR, which all of these use the methods that Tristan brought up earlier, the iterative bounding box method, and then the 2-stage DETR, each of them which having a different backbone, each of which getting stronger until the final one, which uses those time test arguments that I brought up earlier. And as we can see, by using a stronger backbone, the accuracy increases, and then using time test arguments, we get the highest accuracy comparable to other state-of-the-art models. So in conclusion, to quickly review our paper, deformable DETR is an end-to-end object detector with DETR as a base. The main innovation from DETR is use of these multi-scale deformable attention models. The use of these models allow for it to converge faster to DETR in showing the improvement in both accuracy and runtime. And then finally, here are our references.